the last problem, we calculated EMF in a circuit due to change in magnetic flux, that is Faraday's law. What if the circuit is closed? If the circuit is closed, a current flows through that one. Let us calculate the current in a circuit due to electromagnetic induction. Let us see the next problem. A coil having N turns and a resistance R is connected with the galvanometer of resistance 4R. The combination is moved from a region of magnetic flux phi1 to a region of magnetic flux phi2 in time t. The average induced current in the circuit is A minus phi2 minus phi1 divided by phi r nt, B minus n into phi2 minus phi1 divided by phi rt, C minus phi2 minus phi1 divided by r nt, and the answer D is minus n into phi2 minus phi1 divided by r into t. Let us see what are the factors given. Initial flux is given, that is phi1. Final flux is given, that is phi2. The change in magnetic flux takes a time t. You have a galvanometer and a coil. Here is the galvanometer, here is the coil. Coil has number of turns n and resistance of r. The galvanometer itself has a resistance of 4R. I have to calculate the current through the circuit if this circuit is moved from a region of magnetic flux phi1 to a magnetic flux of phi2 in time t. The total resistance of the circuit, effective resistance of the circuit is, as these two are in series, R plus 4R, which is equal to 5R. And the EMF induced is equal to minus change in magnetic flux divided by time taken, which is equal to minus magnetic flux finally is phi2 minus magnetic flux initially is phi1 divided by phi2 minus phi1, time taken is t. Current, as you know, is equal to EMF divided by resistance, which is equal to minus phi2 minus phi1 divided by t divided by r. Divided by r is divided by phi r. As you have n turns here, I should write a n here because E is equal to minus n d phi by dt if the number of turns is n. This gives you minus n into phi2 minus phi1 divided by phi r into t. The answer is minus n into phi2 minus phi1 divided by phi r into t. The answer is B. Let us move on to the next question. The question is, the field line for a particular field is shown in the figure. The field cannot be velocity of a fluid, induced electric field, magnetic field, electrostatic field. The field is like this. As you can see here, this has a curling effect, rotational effect. Any field can have such curling effects if closed integral that field dot dl, that is closed line integral of that field, is not equal to 0. If that is equal to 0, then that cannot have this curling effect, this cannot have curls. As you may have seen in some rivers, it has some rotational effect, therefore, velocity of a fluid cannot be the answer. Induced electric field, as it is produced by a magnetic field, this has curling effects, therefore, this cannot be the answer. Magnetic field, as I have studied, magnetic field forms closed loop, therefore, this cannot be the answer. The answer is electrostatic field. Electrostatic field, this implies that the field is non-conservative. The first three fields are non-conservative fields, therefore, the line integral does not become 0. For an electrostatic field which is conservative, A dot dl is equal to 0, I mean E dot d equals 0, therefore, it is a conservative force, therefore, it cannot form closed loops. The answer is D, electrostatic field. In electromagnetic induction, whenever there is a change in magnetic flux linked to the coil, there is an EMF. If the circuit is closed, there is a current. If there is a current, there is some flow of charge. How do you calculate the flow of amount of charge that is flowing? Amount of charge that is flowing through a circuit is equal to change in magnetic flux divided by the resistance of the circuit. Let us solve one problem on the charge that is induced in a circuit due to electromagnetic induction. Let us see the next question. Magnetic fluxes linked with the circuit at two instants of time are given by 2.5 into 10 power minus 6 Weber and 5 into 10 power minus 7 Weber. If the resistance of the coil is 5 ohm, the charge flowing is A 4 microcoulomb, B 0.4 microcoulomb, C 40 microcoulomb and D 0.04 microcoulomb. Charge flowing, charge induced is equal to mod delta phi b divided by R. That is to take just the positive sign, which is equal to phi 2 minus phi 1 divided by R inside mod sign, which is equal to, I write the mod sign here, phi 2 is 5 into 10 power minus 7 Weber, which is 0.5 into 10 power minus 6. I make that 0.5 in 10 power minus 6 because this is 10 power minus 6, I have to subtract that one. Phi 1 is 2.5 into 10 power minus 6 divided by resistance is 5 ohm, that is 5 here. I get 0.5 minus 2.5 is 2 into 10 power minus 6. You have a minus sign here, but as you have magnitude only, mods, you take positive sign only, divide by 5, which is 2 by 5, which is 0.4. 10 power minus 6 is micro. Charge, that is coulomb. The answer is 0.54 microcoulomb. The answer is B. The next thing we are going to discuss is Lenz Law. According to Lenz Law, whenever there is a production of EMF in a coil, there is a current in the coil. The polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that causes it. That is, if you have a coil and if you bring a north pole of a magnet towards it, the coil becomes north pole to oppose you. If you bring south pole of a magnet towards a coil, it becomes south pole and repels you. And if you take away south pole away from the coil, it becomes north pole to attract you. That is, it opposes any change in the motion of the magnet with respect to it. Let us see some problems on Lenz Law. Next problem is here. The plane of a rectangular coil is kept perpendicular to a magnetic field as shown. If the magnetic field increases, the direction of the induced current in the coil is clockwise, there is no current, anti-clockwise, insufficient data. How do you produce such a field? I will tell you how fields are represented. This is a field coming towards you away from the board. This is a field that is going towards the board. To produce such a field, I have to keep a north pole here, north pole of a magnet here, south pole would be somewhere here. You keep the north pole of the magnet here. To increase the current, you have to move the magnet towards the coil. If you move the magnet towards the coil, you are moving north pole of the magnet towards the coil. Therefore, this coil would become north pole, that is an anti-clockwise current flows through the coil. The answer is anti-clockwise, C, anti-clockwise. Let us have some more insight on this. If the current decreases, if the magnetic field decreases, then there would be a clockwise current flowing through it. If the area increases, then there would be anti-clockwise current. If the area decreases, then there would be a clockwise current. If the case was different, suppose the magnetic field was like this, that is coming towards you. If the magnetic field increased, then there would be a clockwise current flowing through the coil. If the area increases here, there would be a clockwise current. If the area decreases, then there would be an anti-clockwise current. If the magnetic field decreases, then there would be an anti-clockwise current flowing through the coil. This is explained on the basis of Lenz Law.